Okay, the final chapter I want to cover this week is identity. So it turns out that first order logic, in and of itself, is a little clunky when it comes to saying two things are the same. And so, how do they introduce this? They say Pavel owes money to everyone. Now, if you make a symbolization key that looks like this, Pavel here and owes money to Y, you could write this sentence this way, okay, for all X, OPX. So the OPX being this Pavel owes money to everyone predicate. Now, that would mean that Pavel owes money to everyone in the domain. But Pavel's in the domain here, okay? Pavel's something that's named. So Pavel would also owe money to Pavel. And that's, again, not exactly what you mean when you say Pavel owes money to everyone. You mean Pavel owes money to everyone that isn't Pavel, okay? So, usually. So, they say it a few different ways, okay? Pavel owes money to everyone else. Pavel owes money to everyone other than Pavel. And Pavel owes money to everyone except Pavel himself. Those all kind of have the same meaning. Now, it's these italicized parts that are difficult to handle in first order logic without more symbols. So what's most commonly done in most books that I've seen and most treatments of first order logic is they add an equal symbol to the logic itself. There are ways around this, but it's common enough and useful enough to have an equals predicate built into the logic itself. So that's what we're going to do. And they say this symbolization key is what we're going to use. Okay, X equals Y stands for the predicate that X is the same object as Y. So they are exactly the same object. So technically speaking, you without more symbols built in, you would not say in logic that 4 divided by 2 is equal to 2. You would not say this. I can write this here. There's from the last video. You would not say 4 divided by 2 equals 2. You would not say that because those are not identical. Okay. Now, they are equal in as much as numerical equality is defined as a certain equivalence relation of rational numbers. But again, that's a technical thing. But I just kind of want to hit the point that logic in the initial parts would not say these are the same because these are technically different items. Although, with enough basic arithmetic, of course, they're equal, right? So now they want to say Pavel is Mr. Chekhov. So they have P for Pavel, that was up here, okay, and they'll use C for Mr. Chekhov, and this sentence would simply be that P equals C. That is, these are the same people. Now with this, we can deal with sentences 2 through 4. So let me bring up the other screen, and so we can keep those sentences on the screen. 2, 2, 1, 2, 2, 1. Here we go. So now each of these sentences are more or less the same. Okay, all the people who aren't Pavel have money owed to them by Pavel himself. So they symbolize it this way. For all X, if it's not the case that X is Pavel, then Pavel owes X money. Okay, you can see how this is better than this original formalization because Pavel doesn't owe money to himself. Can you even do that? So, if you want it to be specifically that Pavel owes money to people that are not Pavel, then you do need this beginning part that sort of excludes Pavel from the list of people that Pavel owes money to. Okay. Now, remember, the negation here, you're not negating X, okay? negations only work on the predicate, so you're actually negating the entire predicate. We might write sometimes like not px. I think we've seen something like this before. And so not x equal p, it's thought of this way. So just realize that, okay? So that's what they're talking about through here. Now, here's one. No one besides Pavel owes money to Hikaru, and only Pavel owes Hikaru money. I think those mean the same thing, right? So we'll use H for Hikaru, and maybe I'm wrong that they're the same. Let's read. So no one besides Pavel owes money to Hikaru, so they symbolize it this way. There is no X such that X is something other than Pavel, and that same X owes money to Hikaru. Yeah, these are the same, aren't they? Equally, 6 can be symbolized as, for all X, if X owes money to Hikaru, then X must be Pavel. Okay. Now that's a case where we again use that implication inside a universal quantifier, and we use the and inside the existential. Now, they say sentence 7 can be treated similarly. They say, do either sentences 6 or 7 entail that Pavel himself owes money to Hikaru? And that's something to think about. They both seem to me the same to me, so maybe I'm missing some of the subtlety here. But let's move on. The important thing is that you can see how this and this could sort of equally arise from that. Okay. Okay. So there are at least. So we want to look at how there is at least one apple, 2 apples, and 3 apples, how these sentences can be symbolized. Can I make those? There they are. They're over here now. So sentence 8 doesn't require identity. So they're going to use A of X to be the predicate that it is an apple. So you just say there exists X, AX, and that's what it means, right? There is an X such that X is an apple. So, you know, a lot of people say that existential quantifier really means there is at least one thing. There could only be one thing, but the existential quantifier doesn't, you can't read it into it any more than there's at least one object of some type. Okay. Now, the second one, there are at least 2. Now, the book rightly says the natural thing to want to do is this. There exists X, there exists Y, AX, and AY. The problem there is because existential is such a weak operator, the Y, there's nothing in here preventing the Y that you say exists from being the X, you see? So, X and Y could be different names for the same object, the same apple, okay? So, this is where equality will come in and kind of throw that out, okay? And so we have there exists X, there exists Y. Both are apples, and importantly, they're not the same, okay? And you need that. Otherwise, you can't rule out the idea that there's just actually one apple. You're just giving it 2 different names. So to say there's at least 2 doesn't just mean you have 2 names that are apples, but rather you have 2 names that are apples that refer to non-identical objects. Okay. Now, how do you do 3? Pretty clear at this point. Okay. You'd have to rule out, that they're the same. So you have X, Y, and Z, all are apples, and X isn't Y, Y isn't Z, and X is not Z as well. Okay. They say here you can't. It's not enough to use. It's not the case that X is Y, not the case that Y is Z. Because X and Z could be the same, right? So it gets really annoying to have to do that a lot, but occasionally you have to do it. And so they say in general you'd have to, it's a mess, okay? A couple others. This one is there is at most 1 apple, and there are at most 2 apples. So, if there's at most 1 apple, then of course there is at least 1 apple. But what they're saying here is that there's not two, right? Or three, or any more than that. And there's at most two. Would say there's two, but not three or four. But there could be maybe one, okay? So sentence 11 can be paraphrased as, "It's not the case that there are at least two apples," okay? And you can think about that. There is at most one is the same as it is not the case there are at least two. So you can go up to where you symbolize there are at least two and just negate that statement, okay? And that's what they do, okay? It is not the case that there are an x and a y that are both apples and not equal to each other, not identical objects. Now they say it can be approached another way, and this would be the universal quantifier kind of approach. It means you pick out an object, it's an apple. You pick out another object, and it's an apple. Then the only way you can do that is if you pick the same object twice. Okay. So when we're doing picking things out with the quantifiers, it's not like you're reaching into a bag and now it's not accessible anymore. It's more like you reach into a bag and you look at it, you make the predicate work, and then you put it in, and then you reach in again. Okay. So this is you can symbolize it this way. If you pick two things called x and y and they're both apples, then the consequence would have to be that they're identical. Okay, that would also handle being symbolizing the sentence that there is at most one apple. So these will actually be equivalent. Again, it has to do with how negations of existential quantifiers become universal quantifiers, and then how the negation of this inside is actually logically equivalent to this. Again, we'll see that. Okay. Again, it would be you negate this and you get an or, and then you negate this and you get x equals y, and not p or q is really equivalent to p implies q. I think, yeah. So that's how that will work. Now, for sentence 12, there's at most two. You can either think of it as not the case that there are three or more, in which case you'd write it this way. Or you would say, if I pick three things, then it's either the case that x is y, or x is z, or y is z. So, if you picked out three things, then two of them had to be the same. Okay, and you don't know which two. You just know that one of the pairs of two would have to be the same, and that's what that or is all about. Okay, now there's exactly one apple, exactly two, and so on. This is really just a conjunction of at least and at most. Okay, if there's exactly one, there's at least one, and at most one. Okay, so they say just that. You put a conjunction, put an and between those two that we had already discussed. That's one way to do it. Another way to do it is this way. Now this would say there is a thing x, which is an apple, okay, and for anything that is an apple, it's the same as x. Okay, that's another way to say there's exactly one. Okay. Now, was one of these better than the other? Not really. Okay, they're both kind of, they both work. Okay, we're not going to really put value judgments. Now they do a similar thing for the two, and then this time they just conjunct one of the sentences for at least and one of the sentences for at most two, and that's fine. But then they say more efficiently, you could say it this way. If you have an x and a y and both are apples and they're not the same, and if you have a z that's different than these because you have a different symbol, possibly different I should say, the z might not be different, then it must be the case that z was identical to one of the previous ones. Again, that's this is starting to get complicated. I mean, look how long this thing is, but it sort of makes sense, okay? Because you're saying x and y are there. If they're both apples and not equal, and then you pick a third thing, then that third thing had to have been one of the other two. That's what it would mean to have exactly two apples in your domain. So they just kind of finish up in this section, and talk about the word like thing and object and sort of this kind of thing. So that is chapter 24. That should be all we cover in the first week back from the virus extra week off. And please let me know if this way of going through the material is useful for you. Because if it's not, and reading the book is just better for you, just go ahead and do that, or let me know. Let me know also if I could do something better. And I'll see you soon.